All right. Okay. Dear participants, good morning, everyone in Brazil. Good afternoon to all of you in the Netherlands. It's a pleasure to be here with you today. My name is Anderson Gamarano, and I work at the International Relations Office of the Federal University of Ouro Preto. To start with, I would like to thank Professors Julia Castro and Guilherme Bregolini from the Civil Engineering Department at UFOP, and also Professors Bruno Salles and Thais Varela from Avans University of Applied Sciences. Without them, this event would not be possible. Thank you very much for the partnership and for your presence here today. Well, as you may know, the Biobased Battle is a product of the Living Lab Biobased Brazil, and for the second time, the battle will be hosted by the Federal University of Ouro Preto and Avans University of Applied Sciences. It's an honor to be here with you and be part of this event once again. Throughout this week, Dutch and Brazilian students with different backgrounds, we work together to solve environmental issues from the industrial sector. Well, now I will give the floor to Professor Julia Castro, who will present Professor André Santos from the Federal University of Ceará. Professor André will be responsible for the introduction of the assignment today. Thank you very much.
Thank you, Anderson. It's great to be here and together with this team of amazing people and the students who are watching us now. So I'm going to present Dr. André Bezerra Santos. He's a professor from the Hydraulic and Environmental Engineering at the Federal University of Ceará. He received his PhD in Environmental Sciences from the Wageningen, it's difficult, University in the Netherlands in 2005, and besides his master's in specialization in ecological sanitation, he graduated in civil engineering with honors at the Federal University of Ceará in 1998. He has a research productivity grant from the Brazilian National Council for Scientific and Technological Development, CNPq, and he has published over 100 articles in international journals, over 250 conference papers, 6 books, 29 book chapters, and 2 patents. Throughout his career, he has won several awards, both from conferences and public institutions, as well as has been chosen as honored teacher over half a dozen times by his students. And he has had many students because he supervised over 130 young researchers in the past few decades. He also participated in several national and international research projects, coordinating a massive network of experts in sewage treatment and other environmental sciences. He has been working mainly in the areas of domestic and industrial sewage treatment, bioenergy, environmental biotechnology, and sanitation management, among others. I could go on here because Professor Santos has done it all a researcher can do, and he has done it with distinction. However, we do have a schedule to follow, so we are very honored that Professor Santos donated us a little bit of his time to prepare this presentation for the opening of our event. So it's with great pleasure that I welcome Professor André Santos to the kickoff of the Biobased Battle 2021. Professor Santos, it's up to you. Thanks.
Okay, thanks a lot, Julia and Anderson, for the introduction. I will try to keep on track about the time, so we may have a good way and opportunity for this approach of a circular economy principles applied to domestic and industrial wastewater. It's a pleasure for me to be here. I would like to thank for the invitation. It's always good to talk about this subject, and always good to talk to the Dutch people that I consider my second country. I lived in the Netherlands for 4 years, and I had an amazing time there. So it's a very good way to have a flashback of my time in the Netherlands, and it's also very important in this field for us in Brazil to learn with the Netherlands, which is a few steps ahead of Brazil related to the resource recovery in many types of wastewater and wastewater byproducts. So I'd like to emphasize the participation of the Federal University of Ceará in the National Institute of Science and Technology on sustainable wastewater treatment, INCT Sustentáveis, which is a national project coordinated by the Federal University of Minas Gerais under this supervision of Professor Carlos Cherncharo. So this subject, my main idea today is to give a very big overview of the possibilities. So I don't have the intention to go deep in some technological route because we have a very diverse audience. So my main focus here is to give an insight of the opportunities in the sector, which I consider a very good way of nutrient recovery, but also opportunities for different business models that can be implemented and promote the wastewater sector inside and outside Brazil. So this subject, the circular economy, offers a very good opportunity inside the sewage treatment and also the wastewater treatment, but not only in the liquid flow, but also in related to biogas reuse, to the water reuse, sludge reuse, and many types of different approaches. I also had the goal to bring some business that I already implemented in order that you can see that this is not a theory. We also have many ways to implement and to improve the technological rules and also the different business models that already are implemented inside Brazil and mainly outside Brazil. Okay, so we have the current scenario of sanitary sewage in Brazil, that our current wastewater treatment plants, they are designed based on environmental legislation. And if well designed, built and operated, we do have high removal efficiencies of organic matter, nutrients, and pathogens, playing a key role in water pollution control. So the lack of perceived financial return with the wastewater treatment plant, we have to pay for the final disposal of the sludge, and sometimes that is taking a very high cost due to the volume that needs to be transported, and also the many kilometers they are far away from the source until the final disposal. The biogas is wasted, sometimes burned, when we do apply some anaerobic digestion process to treat the wastewater. And the treated liquid is disposed in a water course, often adding an unwanted residual of pollutants and contaminants, because we have sometimes the disposal of raw sewage. Unfortunately, in Brazil, we have sometimes the collection and the disposal of raw sewage. And sometimes when we do have a wastewater treatment plant, the efficiency is not very high. Sometimes is limited to the organic matter removal. And sometimes we are causing environmental problems due to the discharge of nutrients and causing eutrophication, the death of fish, and changing the ecosystem that is based on the water. So we in this scenario, the biogas is simply burned. When it is burned, sometimes is being released to the atmosphere, and we do know that methane is more problematic to greenhouse effects than the CO2, more than 25 times. We have sometimes the use of inefficient burners. We do call flares, which is used to transform methane and CO2 in order to decrease the problem of methane release in the atmosphere. We sometimes we have problems of odor and methane emissions, because sometimes the methane is in the liquid phase and not in the gas phase, which is not reaching the flares sometimes. And we have potential energy loss, because sometimes this high fuel content of methane is not reused. So, and related to the liquid phase, we have the effluent release to the water courses. We have a loss of nutrients because the nitrogen and phosphorus in the liquid phase that could be reused for agriculture and for many other purposes. They are released, and we are causing water pollution. For the sludge and other solid waste from the treatment plants, we are sending them to landfills, dumps, or even rivers. We have the cost for transportation. We have the emission of greenhouse gases. And of course, we have the reduced landfill service live. So the idea is transforming the conventional wastewater treatment plants and sustainable wastewater treatment plants in order to consider the liquid instead of sending to the receiver body. We consider the water as a resource and promoting the reuse of water. For the solid phase, instead of sending to the sanitary landfill, we consider the sludge as a very good fertilizer that can improve the soil properties, decreasing erosion processes, increasing the water retention, and subsequent use by the plants. And for the gas, and also for the solid, we may use as a fuel, for instance, applying the anaerobic digestion and or sometimes other technological process, for instance, pyrolysis, that can convert this solid and energy. And also for the gas phase, instead of burn the methane, we could use as energy, thermal, or sometimes electrical energy. So the main goals for this resource recovery is to contribute to the planet limits. Here we have many indicators of the planet limits. So we have ocean acidification, nitrogen cycle use, and many other topics. And here we have the green zone. And we can see from this picture that many of these parameters are above the limit. For instance, nitrogen cycle. And for phosphorus, we have very close to limit. And we have a problem for phosphorus that is not a renewable source. And we don't have a technological way to produce phosphorus. It's different, for instance, from nitrogen, that when we use the Haber-Bosch process, we can convert the nitrogen in the gas to ammonia. So for phosphorus, we need to think ways of returning this nutrient to the food production. So this planet limits, they point that they need to recover resource from the sewage treatment. So this is a paper published in Nature in 2009. And there is a very bad scenario that, for instance, in 100 and 150 years ahead, we have a phosphorus limitation for food production, and we have to accomplish them with the growth, the population growth, and we have to give food for this population that is growing every year around the world. So this kind of resource recovery is also in line with the Sustainable Development Goals, especially in the topics of clean water and sanitation, sustainable cities and communities, climate action, and also affordable and clean energy. So when we think about the biogas reuse, we are reaching this 7 goal of the SDG. So related to the sanitation conditions in Brazil, we have that 43% of the sewage is collected and treated, and once more, this treated sometimes is only to remove organic matter. We actually, a few of the treatment plants in Brazil are designed and operated well to remove, for instance, nutrient and phosphorus. So 18% of the wastewater is collected and discharged untreated in the receiving body. 27% is not collected and treated. And we do have around 12% of individual solutions. This is a new report published in Baiana, and as here is in the Atlas Esgotos, is Wastewater Atlas. It's a Brazilian publication. And we have a very different scenario in the Netherlands, in which the wastewater treatment coverage is almost 100% since 2008. We have around 90,000 kilometers of sewer lines. We have 25 district water boards that together manage 350 sewage treatment plants. And when we consider the industrial wastewater, sometimes the industries, they are performing a kind of pre-treatment, and when they are not reusing the wastewater is discharged in the sewers, but they are already treated by the companies. So the question is, can sustainable wastewater treatment plants help to make the universalization of sewage collection and treatment in Brazil, for instance? And I say yes, it's a very good way to decrease the operational costs and apply this circular economy concept in order to decrease the operational costs and promote sanitation inside and outside Brazil. So when we think about this application of circular economy on wastewater treatment, we need to understand that sometimes the wastewater, most of the wastewater is collected segregated, is all the different flows of wastewater generation in a household is collected in different pipes and is transported to a decentralized or a centralized wastewater treatment plant. So it's a non-segregated collection and transport and treatment. But sometimes when we apply the concept of ecological sanitation, we may consider this wastewater in a segregated way. So, and we split the different flows as gray water, yellow water, brown waters or water, and black waters. So the gray water is everything that is generated in a household that is not coming, for instance, from the toilet. So we think about pipes and the flow of wastewater in a household, and sometimes we treat separately this flow, and we may promote the reuse, for instance, of gray water for cleaning for irrigation purposes, and sometimes we are pumping back to a second water tank and flushing the toilet with this water. Sometimes when we apply this concept, we decrease the water demand in a household and also the amount of wastewater discharged in the sewer line, decreasing therefore the costs for the people and for the condominium, etc., etc. Especially when we live a water crisis that sometimes is increasing the tax for the water consumption and wastewater collection. And when we apply, sometimes we are separating the urine. It's a very good biofertilizer that can be treated and reused as to increase the food production, for instance. The brown water is the feces without the presence of urine, And so, sometimes when we have both in the same toilet, but sometimes diverting the gray water, we have the black waters. Okay? So if we have everything mixed and collected and transported and treated, we have a non-segregated wastewater treatment. So if we think, let's split up all the flows in a household, we do need to use this kind of urine diverting toilet. So the urine is collected here, the feces is collected there, and sometimes we have a dry toilet. When we think about to save water, and sometimes water is a very scarce resource, especially in semi-arid areas like my state, the state of Ceará. And this is very important sometimes, this kind of approach to save water and reuse the different nutrients in a separate way that is sometimes is decreasing the complexity of the wastewater treatment and increase the opportunities of resource recovery. So we have different types of toilets that could be used, for instance, with the urine diverting toilet, dry and water toilet, the storage of the urine sometimes, and the transportation of the urine to the field. So sometimes this transport is the limiting step because we have a very big volume of urines. Therefore, sometimes the development of the technology for the water evaporation and urine concentration sometimes is helping a lot to promote the reuse of urine to increase the food production. So this is only a slide showing the use of urine as a biofertilizer. So zero urine, this amount of urine and this amount of urine, and we see the subsequent increase of maize production in this slide. And urine is, as I told you, is a very good biofertilizer. It's concentrating most of the nutrients. So here we have urine in orange. So 87% of nitrogen is in the urine, 50% of the phosphorus, and about 54% of potassium. And for the feces, we have that the feces contains a part of the phosphorus and a part of the total organic matter. Almost 50% of the organic matter expressed in terms of BOD, biochemical oxygen demand. But the gray water is accounting for most of the volume generated in the household, about 50,000 liters per person per year, when the urine is accounted for 500 and feces is accounting for 50 liters per person a year. And sometimes we, after the treatment, which is simply to store the urine for about 30 to 60 days, the urine can return to the field for food production, replacing the fertilizers, the commercial fertilizers that sometimes are very expensive. So it's a very way to produce locally the bionutrients, the biofertilizers, and return them to produce food. Sometimes, as I told you, the problem is in the concentration of the nutrient, and there is some research to use, for instance, the solar parabolic concentrator to evaporate the water in the urine and concentrating the nutrients to be transported to the field. Of course, this kind of approach requires a very complex understanding of the different barriers in order to separate the nutrients, the excreta, to use the different excreta and nutrients, but also to guarantee the safety of the users and the safety of the workers that will work with the handling of the food, with the urine application, with the different irrigation project. So it's very important to understand also the risks and to decrease the risks of such practice. So the resource recovery, the size matters, of course, because when we think about a circular economy model of a big scale, we have a decrease of the investment costs compared to very small scenario. When we divide the cost by, let's say, cubic meter of reactor of anyway, so that it's very important when we think a circular economy model to think about the scale, to think about the public, to think about the clients, to think about the costs, to think about the market, because everything is very important for the sustainability of the circular economy model. So when we think about wastewater treatment, I would like to separate what I mean for micro wastewater treatment plant, small, medium, and large size wastewater treatment plant. So here you can see the number of people involved and the subsequent amount of wastewater generated in liters per second here. So when we think about a large scale, is, for instance, over 100,000 inhabitants. For instance, when we think about biogas reuse for electricity generation, sometimes the equivalent population should be higher than this number. When we think about biogas reuse for heating purposes, the number should be around 10,000 to 100,000 inhabitants. And this flow that is considered for this kind of purpose. So it's very important to keep on track the amount of people or the organic load involved. That is, of course, result in a higher or lower biogas, for instance, production in a treatment plant. So when we think about sewage composition, 99.9% of the sewage is water, and 0.1% is solids. So when we think that the organic matter present in the wastewater is a very rich source of chemical energy. So when we think about this organic matter and this energy, for instance, in the wastewater produced in Brazil, this organic matter energy could supply around 42 gigawatts hour per month, which is equivalent to supply this amount of households. So it's a very important way sometimes to decrease the emissions and promote the reuse of this energy. When we think about the nutrients present in the wastewater, for instance, if we consider the macronutrients, nitrogen, phosphorus, and sulfur, the amount of nutrients present could be enough to have this amount of nitrogen, phosphorus, and sulfur per year, which is equivalent to reuse these nutrients in about 48,000 hectares per year. So the use of anaerobic digestion could be a way to promote the wastewater treatment, to recover this chemical energy present in the wastewater, for instance, for energy in the form of biogas, which is usually for domestic sewage. 70% of the biogas is composed by methane, which can be reused as a fuel. And the nutrients present could be in the liquid, for instance, could be reused for food production, and the sludge generated in the treatment plant could be reused for also for food production to recover degraded areas, among other possible use. So when we think about different technological routes for wastewater treatment, we may compare, for instance, the activated sludge process, which is very common, for instance, in the Netherlands and in Brazil, for instance, in São Paulo, Rio, sometimes when we have a very dense population and we have lack of space. But it's a very efficient process, but it's consuming a lot of energy. So we have this consumption of 25 kilowatts hour per inhabitant per year. And if we apply, for instance, the anaerobic treatment, the USB reactor followed by a trickling filter, we have, instead of consumption, we have a production of about 15. So we decrease the consumption, which is increasing the operational costs, and sometimes we are making the treatment plant self-sustainable in terms of energy, and sometimes we are able to sell what is not used in the treatment plant for the electrical company, for instance. So if we compare these two technological treatments routes, the AD process here is low energy demand and possibly zero. We do have a lower sludge production when we use the anaerobic process compared to the aerobic process here of activated sludge, for instance. We have the operation costs about 10 times lower, and we have the preservation of nutrients in the effluent, which is very important for reuse of these nutrients. So over the 2015 to 20 last years, there was a development of the aerobic granular sludge, AGS system in the Netherlands by these two persons, Professor Mark van Loosdrecht and Merle de Krook from TU Delft, which decreased the aerobic treatment costs, let's say, and also footprint. So we have as a very advantage of the AGS process, 35% reduction in power consumption, 75% reduction in area demand or footprint, lower investments costs, operation and maintenance costs, higher removals of simultaneous organic matter, nitrogen and phosphorus in a single reactor, and that works as sequencing batch reactor, SBR process. And also there is the possibility of resource recovery. It's patented as the name of Nereda. It's commercialized by the Royal Rosconing Dutch company. So here we have a picture of AGS biomass. So here, if we can cross this granule, we may have the different activities of heterotroph bacteria, nitrogen removal bacteria, nitrification, denitrification, phosphorus removal. So my idea is not go deeper in the microbiology here, but to give, as I told you, a very big picture of the different possibilities. So this nutrient removal and also the resource recovery is based on the extra polymer substances formation. We call EPS as a kind of biological glue that is formed in around the cytoplasm of the cell. And depending on the formation of the EPS, we have the different possibilities of resource recovery. For instance, many bacteria can produce the alginate-like hexapolysaccharides, in the EPS structure. Sometimes they are forming a tryptophan as a kind of amino acid. And here we have the very good capacity of solids removal in the wastewater treatment compared, for instance, with the activated sludge process. So the AGS biomass is having a higher EPS production and therefore a higher capacity of nutrients and other toxic pollutants present in the wastewater. So, and the different possibilities of water and also resource recovery, we have the alginate, we have the tryptophan, we have the struvite kind of mineral present in the wastewater that we recover struvite during phosphorus removal and treatment in the treatment plant. So we add magnesium in order to combine with the phosphate and ammonium present in the wastewater in order to form this compound, which is the struvite. So we have the need to develop technology to remove the struvite of the treatment plant. And also, we may have the possibility of forming in the treatment polyhydroxyalkanoate, PHA, which is formed inside the cell, is different from the alginate and tryptophan, which is formed in the EPS outside the cytoplasm. So the PHA is a kind of bioplastic that can be used in the petrochemical industry in order to replace the petroleum-based chemicals. So, can we recover some resources from the agro-industrial wastewater treatment plants? Yes, and I'm showing you some pictures of the production of pulp and paper, wastewater, milk products, and also some brewery. That's I pointed brewery and pulp and paper wastewaters in the assignment because they are very important inside Brazil and also in the Netherlands. So it's a very good way to think about resource recovery for this kind of streams of industrial wastewater. So this is in terms of population equivalent based on the COD load, is the product of the COD concentration by the flow, which is the concept of load. So we see almost 4.6 billion people in terms of population equivalent of pulp and paper wastewater around the world, and brewery accounting almost for 500 million people in terms of population equivalent. So this resource recovery can be, we can apply the AD process, the traditional AD process to form methane, to convert the organic matter present in the wastewater for methane, or we can think about different ways of resource recovery, for instance, hydrogen, when we block the methane production in the bioreactor and we increase the hydrogen production in the bioreactor, or we may think about the possibility to convert the organic acids formed here, the small organic acids formed, for instance, propionate, butyrate, acetate, to have a chain elongation process and producing medium or sometimes high carboxylic acids, for instance, caproic acid. That sometimes is the goal in many industrial process that is already implemented in full scale. So the main challenging for this kind of approach is, of course, to inhibit the hydrogen and the methane formation to form the long chain or medium chain carboxylic acids, and also to separate from the liquid, and also to apply the purification step in order to increase the application, the application of this GCAs, medium and high CAs, in the industry. And there is a Dutch company called Chain Craft that is already implemented this carboxylic acid platform in order to produce many types of fatty acids, but they are forming the acids and they are selling in the demonstration facility. The acids are selling as a salt in a powder form. So there are some plans to develop a technological platform to convert the organic matter in acids that can be commercialized in the liquid phase, so to be converted to alcohol or ester derivatives, for instance, in the chain craft industry. So here is the picture. We do have the fermentation step 1 that is related to hydrolysis and acidification. And we do have another step here related to the chain elongation process in order to increase the number of carbons. So we have the C2, the acetate, or C3 propionate. We incorporate carbons in order to have as a final carboxylic acid, for instance, the caproic acid or caprylic acid, that depend on the number of carbons incorporated in the process. And of course, that will depend on the industrial use. So another things to be recovered from the wastewater, we could think about energy, phosphate, sludge, bioplastics, proteins and biopolymers, fibers. For instance, in the Netherlands, they are recovering the cellulose from the wastewater because there is the habit of sending the toilet paper in the toilet. Is different in Brazil, that we are not using this. Actually, our systems are not designed, and also the quality of our toilet paper is not in a good quality or produced to be sent by the toilet system. We can also have the metals possibility of recovery, and also water and many other things that could be recovered. I'm putting here in red because these are the ones that, in my opinion, are most ready to be implemented, for instance, in Brazilian wastewater treatment plants that, as I told you, we are sometimes, we are a few steps than what the Netherlands is reaching and is implemented nowadays. So many possibilities, for instance, for the AGS, aerobic granular sludge, reuse in the treatment plants. The liquid phase, the water to be reused. The solid phase, for instance, phosphorus, alginate-like exopolymers, tryptophan, and other uses in the chemical and the petrochemical industries here. And for the solid phase, for instance, to implement the anaerobic process or other thermal conversion process to recover this sludge as energy. So this approach is already implemented in the Netherlands, for instance, in these two treatment plants in Zutphen and also in Nete in the Netherlands, that are using the AGS system and recovering the ale or ale or other biopolymers produced by the wastewater treatment and the sludge collection and reuse of this sludge. So this is called this bioproduct is called Calmera. So is implemented by the Nereda treatment plants. So there is a goal to use and to recover many tons of Calmera per year and selling this product to the industry. So it's very important to have this change of product generation, recovery, and a very good customer to sell the product. So, and the Netherlands is applying this kind of energy and resource factors in many different treatment plants to reuse the wastewater as a heat recovery process, or sometimes nutrient recovery process. For instance, using this activated sludge system. This heat can be recovered, can be reached by using the anaerobic digestion process, or sometimes using the incineration process. So the Netherlands is recovering 80 to 90% of the phosphate in the form of struvite, and it's very good this kind of recovery, because struvite, the release of this nutrient in the field is lower than the commercial fertilizer. Is very good for the crops. This is low release, and the solid waste generated in the treatment plant, the sludge, can sometimes after the AG process, or sometimes that is used, the sludge is incinerated, only the sludge, or sometimes the sludge together with the solid waste generated in the country. So, and the ashes, sometimes the ashes are converted and sold to Germany to use in the mines. Okay, so the possibilities we have: the water, the biogas as energy, cooking, heat generation, transformation to biomethane, burning flares, and when the biogas is transformed to biomethane, we have the injection in the natural gas network. We may have the possibility of the use of microalgae to produce biofuels, animal nutrition, human nutrition, to be converted in cosmetics, drugs, fertilizers. So many opportunities. And we have the possibility of using as open pond like this one, or photobioreactors. And we have the challenging of microalgae separation and reuse of this microalgae. And the sludge can be used in the soil, as I told you. So in 2007, 40% of the sludge produced in the EU was applied in agriculture, with large difference between individual countries. And in Brazil, only a few sludge is being recovered. For instance, Paraná has some experience on this reuse of sludge, but very low use of sludge in Brazil. We hope that now, after our legislation was changed last year, we have a higher experience of sludge reuse for soil conditioning and improving the properties. And finally, we have the possibility of resource recovery in micro wastewater treatment plants. So we may combine the housing deficit with a project in order to increase the resource recovery in small treatment plants. So, for instance, if we think about a building, the best resource recovery that can be used is the water, because we don't have the need for nitrogen and phosphate and energy, because the production is very low. So, but if we think about a different approach, for instance, here is when we use the gray water, transforming the gray water in almost a purified water to be used in the toilet in a small wastewater treatment plant. We need to perform some costs analysis to see the real possibility and the payback of the investment. But if we apply the treatment plant in a scenario like this, we may have the possibility of using a higher amount of nitrogen, phosphate, sludge, and water. So in this way, we increase the possibilities of resource recovery in wastewater treatment plant. Okay? So as a conclusion, we need to increase our experience on resource recovery. The resource recovery depends on the local need, the business model adopted, and market. Resource recovery depends on the size and technological route adopted. It's a way to universalize the wastewater collection and treatment in Brazil. And many technologies are available, but sometimes of high cost. So we need technology development. So it's just to think that the best of me is here in the toilet. So the urine, the feces, and the separation of sources is very important for nutrients recovery. We have the toilet as a way of thinking about politicians and other aspects. It's a pleasure to present this YouTube channel, Conversa sobre Saneamento, etc., that I created last year in order to promote the resource recovery and sanitation issues online. This is a link for a book. And thank you for your attention. Obrigado, danke well.